you for organizers for inviting me. Today I'll talk about Milnor numbers or projective hypersurfaces and chromatic polynomial of graphs. So these are the two prerequisites we should know that we are interested in this talk. If we have a finite sequence of real numbers, then we say that such a sequence is unimodal if it first increases and then after some point then it decreases. And the second condition we're interested in such a sequence is low concavity. It says that if you pick up any point in the sequence and square it, then that number is larger than the product of the two terms beside it. And it is easy to check that the second condition is usually stronger than the first one, which means that if the sequence is no internal zeros, then low concavity implies unimodality. So here's the reason we are interested in such a concept, because those sequence mysteriously appears in many different mathematical objects, and it's usually hard to understand why they appear to be so. And this is the simplest and the most important example of such a sequence, the binomials coefficients. So if you expand 1 plus x to the 5, then you get a certain sequence of numbers 1, 5, 10, 10, 5, 1. As you can see, they first increase up to some point, and then after that it decreases. Moreover, this sequence is low concave, which means that if you square 5 in the middle between 1 and 10, then that will give you 25, which is larger than 1 times 10. And that works for any other choice. And we are interested in the low concavity property of a chromatic polynomial of a graph. So what is a chromatic polynomial? So if you have a finite graph G, and if somebody gives you a number Q, then you can count the number of ways that you can color G with Q colors. And what's amazing about this function is that this function is in fact a polynomial in one variable Q with integer coefficients, and those integers happen to alternate in sign. So for example, the very basic question in graph theory says that if G is planar, then whether the value of this polynomial at 4 is positive. So here's a very first example. If you have a graph on 4 vertices and 4 edges, then you can count it in many different ways and easily conclude that the chromatic polynomial of this graph can be written as follows. So our coefficients are 1, 4, 6, and 3. So it increases first, and then after some point it decreases. And moreover, these sequences form a low concave sequence. For example, if you square 4 in the middle, between 1 and 6, then 16 is evidently larger than 1 times 6. So here is the conjecture we are going to attack in this talk. This Reed in 1968 conjectured that for any graph, finite graph G, if you write down the chromatic polynomial in that way with alternating signs, then we know that such a sequence A0, A1 to AP form a sequence of positive integers, and he conjectured that such a sequence is unimodal. And soon after that, Rota generalized this conjecture in a much more general setting of matroids. So let's recall that if we have a matroid M, then there is associated lattice of flats. So in this talk, we'll think of matroid as an arrangement of hyperplanes in some fixed vector space. For example, if you have 4 hyperplanes like this, then you look at all the flats formed by taking intersections of these hyperplanes. And the diagram, the pose that appears there is a typical example of a Hasse diagram. And associated to such a matroid, there is one nice natural way to count things, which generalizes the chromatic polynomial of graph. I will since this is a discrete geometry seminar, I'll not repeat the kind of complicated definitions of this, but you can believe that this is one of the very natural ways to count things. And the chromatic polynomial of a graph is a particular instance of a characteristic polynomial associated to a matroid. And in this context, Rota generalized the release conjecture in this setting. So if you have a matroid M, then there is associated characteristic polynomial, which you can write it in the same way. Then AIs form a sequence of positive integers. And Rota conjectured that such a sequence is unimodal. And after that, Welsh even more generalized this conjecture by saying that such a sequence should be, in fact, low concave. And this is the version of the conjecture we are going to attack. There are a lot of partial results for Reed's conjecture, known for many class of graphs. And recently, Linder and Markstrom verified computationally that this Reed's conjecture holds for all graphs with less than or equal to 11 vertices, which is a serious computation because not only because there are a lot of graphs with 11 vertices, but even when you're given just one graph, it is not so easy to calculate this chromatic polynomial. So there was a speculation that this type of the conjecture will not be true, but I'm claiming that it is. So let's surprise Professor Stanley. This is my claim. Rota-Welsh's conjecture holds over a field of characteristic 0. More precisely, which means that I'm saying that whenever your matroid can be realized as a set of vectors inside a vector space over a field of characteristic 0, then the characteristic polynomial of such a matroid is always low concave. In particular, Reed's conjecture on graphs is always true because we know that if we have a finite graph, then the chromatic polynomial of that graph is the characteristic polynomial of some matroid realized over any field. So our proof is a combination of three things: Morse theory, and the convex geometry, and commutative algebra. So I'll give a brief outline of the proof, which goes as follows. So let A be an arrangement. And by an arrangement, I mean that you have a vector space, say Cn, and you have a finite number of hyperplanes inside Cn. It could lie in a very complicated way. But we know that the characteristic polynomial of such a hyperplane arrangement, or a matroid, and we are interested in coefficients of that polynomial, and those coefficients are known to be the Betti numbers of our complement of hyperplane arrangements. So those Betti numbers are the ones we'll attack to show that they are low concave. This was a theorem of Ulrich Solomon going back to 1980s. And starting from this second part, this new argument goes, we'll first show that by a more theoretic argument that this Betti numbers of the complement of our hyperplane arrangement is related to the number of solutions of a polynomial system. And this is essentially the index counting in Morse theory. And we have n many polynomial systems corresponding to n many Betti numbers. And we'll show that such a number is low concave. And it is very classic in algebraic geometry that number of solutions in a polynomial system has something to do with the growth of the graded algebras. For example, if you have a projective variety, and then associated to that there is a Hilbert polynomial, and Hilbert-Samon theory says that the leading coefficient of that polynomial counts the degree of the projective variety, which means that just the number of solutions when you get if you intersect with the general hyperplane or general plane of right dimension. Okay, so we are interested in the combinatorial object, and we pass it to the Betti numbers. And I'm claiming that we can count those Betti numbers by counting the index of a Morse function, and then such index of Morse function has something to do with growth of graded algebras. And then what we do is this. It is classic theory of error which says that if you have a good algebras, the so-called toric algebras, then the growth of such algebra is measured by a volume of the associated polytopes. And there is a recent construction due to Okenkopf, which is, in essence says that you can do that process for arbitrary graded algebras, not just toric algebras. And this is not a complicated thing. This is essentially just a Grabner theory. If you have an arbitrary algebra, then there is a way to pick up leading terms in a consistent way so that it succeeds to measure the growth of those algebras. And once we are reduced to the toric case, then the classical theorem Ehrhart says that such a growth can be represented by a volume of a polytope. So we reduced the question of this thing. You have two polytopes, and you're measuring the volumes of the Minkowski sums of those polytopes. Now it is even more classical theorem of Minkowski says that this volume function defined on the space of all polytopes is always Euler concave, and that's where our conclusion comes from. So I'll be more specific, and I'll show that the Betti numbers of the complements are the so-called mixed multiplicities of certain ideals in a polynomial ring. I'll explain what that highlighted word means in a short time. And second, we'll show that mixed multiplicities always form a low concave sequence under certain conditions. And I'll specify what that certain condition is. So that will conclude our theorem. But before that, let me introduce what is the mixed multiplicities of ideals. So our setting is this. Of course, you can do it in a much more complicated setting, but this will be sufficient for our purpose. Let S be a polynomial ring in m plus 1 variables, and I'll write m for the maximal ideal generated by the variables. And let J be a homogeneous ideal of S. Then, what we are interested in is the growth of the vector space dimension formed by taking these quotients. So whenever someone gives you a positive number u and v, then you form a vector space taking product of m to the u and j to the v. And that is a finite dimensional C vector space in this case. So you can ask, what is its dimension? And it is known that such a function is essentially a polynomial in two variables. Just like in the one variable case, it's just a slight generalization of the Hilbert polynomial. So this polynomial happens to measure the dimension of our base ring S. And so we can write the top dimensional part just as we formulate the Hilbert-Samuel multiplicity, and write down the top dimensional part of our two-variable polynomial in this specific way. And by writing this, I'll define the number EI MJ.
This n is different from the n there.
Well, in this case, it is same. It is a theorem that it is the same, right? If you have a degree of the Hilbert polynomial measures the dimension, right? In this case, if the j is non-zero whenever that happens, then the degree of this polynomial is in fact n. Then this EI MJ are non-negative integers, and I'll say that this EI MJ is the mixed multiplicity of m and j. More specifically, I'll call this thing as a ith mixed multiplicity of m and j. It measures the growth of this algebra. So we have n plus 1 numbers. Here's an example. Suppose our ideal J is of power of the maximal ideal n. Then we are interested in the growth of this vector space. But in this case, since J consists of all the monomials of degree R, we can easily conclude that this vector space dimension is simply the number of monomials of degree U plus RV, right? So we can combinatorially count that, and this P mu V happens to equal something starting with leading term U plus RV to the power of n. And if you count in this specific way with these denominators, then we see that our mixed multiplicities form this geometric series. 1, R square, blah, blah, blah. So for future this as a reference, let's remember this case. J is m to the power of R. Then let's look at this sequence, 1 to the R square, and so on. This sequence is the only sequence which is both low concave and low convex. And I'll say that this is, in essence, the only case. So it was a theorem of Tessier back in 1970s. In the setting before, if J is n primary, which means that S quotient J has finite vector space dimension, and in that case, these sequence of mixed multiplicities form a low convex sequence. This is exactly the opposite of what we want. And you can verify theorem of Tessier in this setting. J is obviously n primary, and so as a consequence of his theorem, these sequences form a low convex sequence. And recently, Trong and Verma showed that if J is a monomial ideal, then these mixed multiplicities are mixed volumes of certain polytope associated to M and J. So as a classical application of convex geometry, which in Alexander Frenkel inequality says that these numbers, EIs, form a low concave sequence. And they ask, in general, if J is not a monomial ideal, but instead height of J is n, whether this sequence form a low concave sequence. So unfortunately, there is a counterexample to this conjecture, but I'll show that when J is generated by elements of the same degree, then this sequence form a low concave sequence. So just for emphasizing, J generated by elements of the same degree is even stronger than the J is just a homogeneous ideal. J is homogeneous, and it can be generated by elements of fixed degree, say 5. So I'll define Milnor numbers associated to projective hypersurface. So Milnor number is usually defined for a germ of analytic germ which defines the isolated singularity at origin. But I'll define the Milnor numbers. I have Milnor numbers. So I have n numbers associated to a projective hypersurface. So let H be a non-constant homogeneous polynomial in n plus 1 variable. And we form the Jacobian ideal generated by the partials of H. Then we look at the mixed multiplicity of M and the Jacobian ideal. In other words, we look at the growth of these algebras. Then we have a polynomial, and we look at the leading term, and there are n plus 1 coefficients, and we'll define the ith Milnor number of H to be the non-negative integer EIMJH. So we have n plus 1 well-defined numbers. If you believe me, since Jacobian ideal of a homogeneous polynomial is always generated by elements of the same degree, these mui's, the Milnor numbers, form a low concave sequence, no matter what H is. And it is well known that such a sequence of mixed multiplicities in general have no internal zeros. So low concavity implies unimodality, which means that it first increases and then decreases. So I'll state the first theorem. And when H is a homogeneous polynomial, then I'll write VH for the projective hypersurface defined by H. So if you have a homogeneous polynomial, then it defines a well-defined set of zeros in the projective space. And I'll write DH for the complement of VH. And also, I'll fix a sufficiently general flag of linear subspaces. P0, P1, and to the Pn. And then, according to this fixed general flag of linear subspaces, I'll write VHI for the ith general section, I-dimensional general section of VH, and DHI for the ith section of DH. With these terminologies, we have the following theorem. The ith section of complement, DHI, is homotopy equivalent to a CW complex obtained from I-1 section by attaching this many cells, our numbers mu I h, many cells of dimension I, real dimension I. So in particular, mu I h can be expressed as a topological Euler characteristic of the difference. And this second part will be important in approach to our combinatorial conjecture, which says that if H is a product of linear forms, which means that its set of zeros is just a bunch of hyperplanes in the projective space, if that happens, this mu I h is not just the number of cells attached in that CW structure, but it's also the Betti number of our complement of projective hypersurface, which means that all the attaching maps are homologically trivial. Well, second assertion seems much stronger than the first, but it's in fact a very easy consequence of the first one, because we already know that these Betti numbers comes from this characteristic polynomial associated to hyperplane arrangements, and this characteristic polynomial behaves very well with respect to a generic section. In other words, if you choose your general hyperplane so that your hyperplane or I-dimensional plane is transversal to all the flats in that matroid, then it is obvious that these first I coefficients are preserved by taking the general linear section. So, because the poset structures are not affected by taking the general hyperplane section. So if you accept 1, then if you attach k plus 1 cell in this thing, then it should not, since the kth Betti number is not affected by that process of attaching, the k plus 1 number of k plus 1 cells attached should be the Betti number. In other words, k plus 1's attaching map is homologically trivial because it should not alter the kth Betti number. So that's where 2 comes from. And here's a little remark. Most of these things are known in various other forms, but most naturally explained as a consequence of the previous theorem. This is the first consequence. This DH, the complement, has a finite CW complex structure, which is kind of not so trivial. And even more, it has a structure of it is homotopic to a CW complex of real dimension n. That's kind of surprising if you haven't already know this as a fact, because DH has real dimension 2n, and I am asserting that it is homotopic to a CW complex with a dimension n, exactly half many. And then, of course, our numbers mu I h can calculate the topological Euler characteristic of the complement, and together with these facts, 2 facts. Number 1 is that this topological Euler characteristic is additive on complex algebraic varieties, which means that you can calculate the topological Euler characteristic by the inclusion-exclusion principle, which is very non-trivial statement, but still is true. And the second fact is that we can effectively compute these numbers mu I h for arbitrary this polynomial h. This is essentially you can reduce it to the Grabner basis computation and do the usual Macaulay 2 thing. Then you can easily calculate those numbers effectively. So combining 1 and 2, our theorem says that we can compute the topological Euler characteristic of arbitrary projective varieties and affine varieties, not just hypersurfaces, due to the additive nature of topological Euler characteristic. So I'm not assuming any condition on the possible singularity of our projective variety. We can always compute it as a number 27 or 42. If you type it in the script, then Macaulay 2 will tell you what that number is.
I'm very concerned about the statement you have made, because if it is a variety over Z, whatever that actually mean by that, but it is discrete, and then what do you mean by topological? Do you actually make a completion over certain kind of embedding of Z into a complex space field or something else?
Oh, so I have written down here Z so that I can actually type it inside the Macaulay 2 in an easy way.
The last sentence is not really making good sense, because well, I guess you probably mean that you want to take a polynomial in Z coefficient, but the variety that is generated is going to embed in a complex case.
Of course. Everything is over C. Just that Z is just easy to, that's the only way how I write it inside the computer. But yeah.
Finite type of Z, for instance, the variety is formed is going to be discrete, and talking about the topological Euler characteristics.
Of course. I'm saying that this H defines a projective hypersurface inside a complex projective space. Okay. And I'm not saying anything outside the complex case. So this is a particular case of interest. If you have a system of polynomials, and suppose that such a system has only finitely many number of zeros. And I'm saying that we can count how many zeros there are, because Euler characteristic in this case is just the number of points. So this contrasts other Macaulay 2 methods, which usually counts everything scheme theoretically. I just count how many there are. I don't care what the multiplicity is. So here's an example. Suppose I have a homogeneous polynomial in 2 variables, x squared, y cubed. So algebraic geometrists will say that, oh, there is 5 zeros of that polynomial, but I'll say that there are 2 zeros in the CP1. So let's see how to compute that number 2. So what I do, I first form the Jacobian ideal. You derive with respect to x, and you derive with respect to y. And then you can easily conclude that the Jacobian ideal is, in fact, xy squared times the maximal ideal. And you look at the growth of this algebra, and you can easily verify that that divisorial factor in front, xy squared, doesn't affect the growth of these dimensions. So this dimension is just m to the u plus v, quotient by one more m. And that is exactly number of degree u plus v monomial in 2 variables, so that our polynomial is u plus v plus 1. So our numbers, mu0 and mu1, are 1 and 1, which you can read off from this polynomial. So our topological Euler characteristic is obtained by taking alternating sum, 1 minus 1 equals 0. And the topological Euler characteristic of this projective hypersurface, which is 2 points, is 2, not 5. And you can easily convince yourself that the exponent up there doesn't matter for this kind of calculation, because in any way they will result in a divisorial factor here, and will not affect the growth of this vector space dimensions. So, okay, mu IH can count. It doesn't count with multiplicities, or it doesn't count correctly or properly or whatever. So here's the example. One more example. If suppose VH is a non-singular hypersurface. Usually we don't assume anything on the singularities, but let's just suppose that. Then the Jacobian ideal should have no zeros. So it should be M primary, and by the theorem of Tessier, which says that if you have a M primary ideal, then the sequence mu IH should form a low convex sequence. So our invariants mu IH form a low convex sequence. But I say that mu IH form a low concave sequence in any case. So we have some sequence which is low convex and low concave at the same time. Well, you can easily check that by hand computation. Mu 0h is 1 and mu 1h is d minus 1. So after that, our sequence is fixed because it's low convex and low concave. It should be a geometric series. 1, d minus 1, and then I should have d minus 1 squared. And then I should have d minus 1 cubed, and so on. So let's look at the particular case. If VH is a non-singular plane curve, then the topological Euler characteristic is obtained by taking alternating sum of that geometric series. So Euler characteristic of our plane curve is obtained by subtracting that number from 3, which is the Euler characteristic of CP2. So the genus of our thing can be expressed as a familiar degree genus formula. But of course, our formula works in arbitrary dimension with no assumption on singularities. So in particular, if our hypersurface has only isolated singularities, then our alternating sum expresses exactly this Milnor-Plucker formula, double point formula, known in various names. So, so what has this kind of thing to do with graph coloring problem? So I'll explain that. So let M be a matroid representable over a field of characteristic 0. This means that matroid M can be realized as a set of vectors or a set of hyperplanes in a vector space over a field of characteristic 0. So all its lattice properties can be preserved by such a mapping. And Welsh's conjecture in this setting says that coefficients of the characteristic polynomial associated to M form a low concave sequence. Why is this? We know this if the field is C. Because if a matroid M is realized on a C vector space, then it is essentially the complex hyperplane arrangements. And in that case, we know that such coefficients are the Betti numbers of the complement of our hyperplane. And those Betti numbers are exactly our numbers mu IH. And mu IH are low concave for arbitrary homogeneous polynomial H. So such sequence is low concave. Well, there is a famous theorem, the famous coordination theorem, which says that this representability of a matroid is, in essence, first-order logic property. Given a matroid M, there is a system of linear and quadratic polynomials with coefficients in Z, such that M is representable only exactly when, over a field, exactly when such a system has a solution over a field K. So what this implies in our setting is that if M is representable over some field of characteristic 0, then it means that this polynomial system associated to M has a 0 over that characteristic 0 field, which means that it has a 0 in the algebraic closure of that field, which means that since algebraic closed fields are complete in the model theoretic sense, a sentence is true exactly when it is true over C. So our polynomial system has 0 over C, which means that our matroid is in fact realizable over C, if it is ever realizable in any characteristic 0 field.
Could you possibly remind us what the definition of the representability matroid is?
So matroid is usually defined by a set of axioms which mimics the linear independence in a vector space. So if I say matroid M is representable over C, then that means there is a map from the underlying set of the matroid, which consists of abstract vectors, to the real vectors in a C vector space, such that it preserves all the post-set structures. So if you have here abstract I-dimensional subspace, then that is mapped to actual I-dimensional C space. So, in fact, we have to prove it over C, but that's all we need. It's true over any field of characteristic 0. In particular, we don't even need this kind of strength, but if you have a graph, then there is a way to associate the graph to a matroid in such a way that the resulting matroid is realizable over any field. And the characteristic polynomial of that matroid is exactly the chromatic polynomial of the original graph, which is just the number of ways to color the graph. So that, I think, so we can now understand why this kind of sequence 1, 4, 6, 3 form a unimodal sequence, or even more is low concave sequence. And there is a bonus from this approach. Oh, before doing that, I like to conjecture one conjecture of my own. So it can be false, but I conjecture that Rota-Welsh's conjecture is false over a field of characteristic P. And I'm not sure how good my reasoning is, but my reasoning is as follows. I know that it is true over a field of characteristic 0. And I know that it is a first order property, which means that if it's true over a characteristic 0 field, then it is true over almost all the primes, if you can translate it. But you cannot prove it for all the primes. And I know that the sequence of our interest has something to do with derivatives. And my final argument goes as follows. These numbers are the mixed multiplicities of the Jacobian ideal. And mixed multiplicities of ideals, following this argument, is in any case low concave. And in order to show that those mixed multiplicities are the number of combinatorial interest, we should verify this certain type of inclusion-exclusion formula, but that involves taking derivatives. So I'm pretty sure that if you are over characteristic P, then there is a good reason that inclusion-exclusion formula should be false. And furthermore, I know that such inclusion-exclusion involving derivatives should be false. If we are in characteristic 2, then it should be false in degree 2, 4, 8, 16, or so on. And there is a strange tendency that if a matroid M is realizable over 2 different characteristics, then it is actually representable over characteristic 0. So we should search this counterexample over characteristic 2 or some other small characteristic, with 2, 4, 8, or 16 hyperplanes, which we can expect of that behavior when taking derivative with respect to the variables. And we should look at the matroids that are only representable over the field of characters 2. And there are a lot of them. I haven't calculated too many of them, but I'm pretty sure if there is a counterexample, then here is what we are looking for. Anyway, let me continue with this bonus. It is of classical interest to bound the Betti numbers of projective hypersurface or its complement. Here's one corollary due to this formulation. It's a very simple example. Suppose we have a two-variable homogeneous polynomial, which is in that sense just a one-variable polynomial. So let's say our polynomial is sparse, which means that there are not all the terms are appearing inside it. Just for example, let's suppose that our polynomial has degree d and has only the first fragment of it. We don't have x to the d minus p minus 1 to the y p plus 1 and so on. Then let's write delta for the standard simplex, one-dimensional simplex, in this case just a unit interval. And let's write delta h for this Newton polytope, in that sense, of h. Let's say 0 to p. Its length is given by this volume of the Newton polytope of h. Then we know that it is easy to check that the zeroth Betti number of the complement, which is just a point, is 1. And the first Betti number of the point is less than or equal to p, because our polynomial has at most p plus 1 zeros, right? We have 1 0 coming from this vector, and we have another degree p homogeneous polynomial which can have at most p zeros. So our complement has a homotopy type of wedge of d minus 1 circles if we have d zeros. So in this case, we have a bound of the Betti numbers in terms of the sparse structure of h. I say that we can generalize this example. Here's a crucial lemma for that thing, which is kind of interesting in analogy with this Tessier's low convex theorem and my low concavity theorem. Here is the comparison. If you have two n primary ideals and one is contained the other, then the arrow is reversed. Say that if I and j are generated by elements of the same degree, then if one is contained in the other, then the arrow is preserved. So, well, if you accept this lemma, then we can easily conclude this bound on the Betti numbers of dh as a corollary. So let h be any homogeneous polynomial in n plus 1 variables, and I'll write delta for the standard n simplex in the n-dimensional Euclidean space, and delta h for the dehomogenized Jacobian Newton polytope of h. And by that, I mean this. You look at all the possible monomials which can appear by taking partial derivative of h. So it's in essence just the Newton polytope of h, but translated by 1 in every direction. And you take the union and convex whole. And I'll write MVN for the mixed volume of n polytopes in Rn. So my normalization is that if you take the volume of the standard n simplex, then I'll say the volume is 1, not 1 over n factorial. In that normalization, ith Betti number of the complement is smaller than mu ih. Of course, because mu ih is the number of I-dimensional cells attached in some CW model of dh. And The second claim is that mu IH is always smaller than the mixed volume of the standard simplex and the Newton polytope of H. So this theorem says that if your original homogeneous polynomial H has few terms, or it has small Newton polytope, then your Betti numbers cannot be large. That is interesting because the terms on the left are intrinsic invariant of a projective hypersurface. But the term on the right, the mixed volume of Newton polytope, is not the invariant. It depends on your choice of coordinate. For example, if you have a very small polynomial, say with one term, then you make the projective linear transformation. Then you have all the terms appearing there. So this part generically goes as large as possible. But for some specific representation of our sparse polynomials, this mixed volume bound is pretty effective. So here's an example. Here's the smallest possible polynomial with one term, product of all the variables. Then delta is the standard n-dimensional simplex, and delta H is Jacobian Newton polytope, which means all the exponents which might appear as a monomial exponent in the partial derivative of H. So these are the ones, 0, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, and so on. So it has a volume 1. And you can compute hard and conclude that the mixed volume of these things are exactly the binomial coefficients of this n choose I. Well, but our complement of the hypersurface, since it is defined by product of variables, it is just the n-dimensional complex torus. So the Betti numbers are exactly n choose I. So our equality back there, this is n choose I, and that is also n choose I. So our equality holds throughout, in this case, for all I and any given n simultaneously. So this bound is sometimes very effective for a given sparse polynomial. That's it.